Everyone, welcome to Theorems talk by Brian Zhang. We'll be talking about fixed parameter algorithms for optimal correlation. Too long. And for today's sponsored in part by Smart Contract Research Forum.
Okay, thank you, Praneet, for the introduction. Today, as he said, I'll be talking about fixed parameter algorithms for optimal correlation in general sum extensive form games. That's a mouthful, but I'll explain what all of that means. This is based on a very recent joint work, and by very recent, I mean one of these preprints literally went on arXiv last week with Gabriele Farina, Andrea Celli, and my advisor, Thomas Zhang. Okay, let's get started. So first, here's a quick outline of the talk. I'll first give an overview of our main results, then I'll dive into definitions about extensive form games. Then I'll be presenting results about two different settings, actually. Fixed parameter algorithms for adversarial team games and optimal correlation in extensive form games. And these two problems turn out to be very related, and I'll explain why as we go along. And finally, I'll summarize, I'll talk a little bit about some experiments and some future research. Okay, let's start with an overview. Our main goal, as I said, will be to develop fixed parameter algorithms for these two problems, team correlated equilibria in adversarial team games, and optimal correlated equilibria in general sum games. Now, a lot of you might not know what most of the words on this slide mean, so now I'll go through this. And then as I said, these are very closely related problems that we'll be using very similar techniques to solve. First, what are games? When we use the word game, a lot of people think about recreational games, things like poker, things like Battleship or something like this. But games also represent real world scenarios. Any scenario in which more than one player is interacting and the agents might have different incentives, different information, so on and so forth, is the game. So for example, you might think of auctions or negotiations or something like this between parties with their own interests. These are all games. Okay, now, what are fixed parameter algorithms? For those of you who don't know, a fixed parameter algorithm is one that, given an input where x is an instance and the pi's are arbitrary integer value parameters, the algorithm should run in time f of the p's times polynomial in x, where f is an arbitrary function. So basically what we're doing is we're narrowing down what the hard part of the problem is. We're saying the hard part of this problem is entirely expressed in these p's. And if these p's are small, in particular if these p's are constant, we should get a polynomial time algorithm out. Okay, and now let's quickly discuss our two settings. The first setting is team correlate. If the p's are constant. If the p's are constant, then f of a constant is a constant, and we're left with only polynomial in x. Okay. If the p's are not constant, then of course the time is going to blow up as measured by this function f.
P could be the dimension of the problem.
Yeah. And I'll discuss exactly what these parameters are for our setting as we go along, of course. Okay, so the first setting is team correlated equilibria in adversarial team games. So what's an adversarial team game? The name says it all, really. An adversarial team game is a game between two teams of players that is adversarial. So if one team is doing well, the other team is doing poorly, and vice versa. And the teams can have imperfect information, they can have more than one player, so on and so forth. These will arise naturally in the real world whenever communication is limited. So for example, in recreational games, for those of you who play a game like Bridge, Bridge is a very well-known example of an adversarial team game. Or in the real world, when there are players colluding or we're trying to defend against collusion, these are all going to be formulated as team games, so on and so forth. I'm not going to elaborate too much on practical applications here.
Are you distinguishing adversarial from zero sum?
No, adversarial means zero sum.
Oh, okay.
Yes. So the
I use the regular term for
that. I mean, adversarial. The two teams are playing strictly against each other. Sure. And okay, so the second setting is optimal correlated equilibrium in general games. So what do we mean by correlation first? A correlated equilibrium is basically, and I'll elaborate precisely on what this means later, a Nash equilibrium where the strategies can be correlated with each other. Different notions of correlated equilibrium exist. We'll be actually using three in this talk. And the three that we'll be using are the so-called normal form coarse correlated equilibrium, extensive form coarse correlated equilibrium, and extensive form correlated equilibrium. I won't be precisely defining these now, but just to give you a sense of where we're going, we have these several different notions of correlated equilibrium that are all different, that we will all develop algorithms for using basically the same tools. And by optimal here, we mean we will want a correlated equilibrium that maximizes a given objective function. Okay. Correlated equilibria also arise quite naturally. In practice, anytime that there's a central entity, say that we'll call a mediator, that can suggest but not enforce behavior. So for example, negotiations, conflict resolution, crowdsourcing applications, things like this. And the first motivation for correlated equilibrium was actually as a relaxation of Nash. When Nash is too hard to find, which it very often is in these general sum games, we want some relaxation that is computationally tractable, and correlated equilibrium arises as a very natural relaxation in this setting because it has a lot of nice properties. Okay. And it also arises, interestingly enough, as the long-term behavior of no-regret learning dynamics. And this is a fairly recent result. If you take certain no-regret learning dynamics, these are known now to converge to certain notions of correlated equilibrium in extensive games. Okay. Let's talk briefly about what prior algorithms are known for this sort of one. Yes.
How should I think of correlation? I don't have a good graph for it yet.
Yeah, a simple example might be, okay, so I have a mediator and the mediator picks a strategy. And after the mediator picks a strategy, the agents will either choose to obey that strategy or not. And a correlated equilibrium is a way for the mediator to pick strategies such that the agents are incentivized to obey. So this, yes.
Maybe I understand something. It sounds like a correlated equilibrium is a subset of Nash equilibrium, but I don't understand how you could have a uncorrelated equilibrium.
It's the other way around. Correlated equilibria are a superset of Nash equilibria. Okay. So Nash equilibria are in particular uncorrelated correlated equilibria. If that makes sense, like correlated equilibria without the correlation part.
Okay.
Okay.
Well, this is the overview,
Yes.
so
Yes.
we're not supposed to understand.
Yes, it's okay if you don't understand exactly what this is. I will formally define everything later in the talk.
So there's an object that is more general than Nash equilibrium.
Yes.
And you're going to solve it.
Yes.
And it's easier to solve than Nash equilibrium.
Yes. Yes. Okay. Both of these problems are NP hard and even NP hard to approximate to within some constant error. So even approximation algorithms are out the window. So we still have to figure out what to even do in this setting. Some special cases are known to be polynomial time solvable. For example, so-called triangle free games, which I won't be elaborating on here. These games include all two-player games with public chance nodes. So in particular, if chance is public, then we have polynomial time algorithms. These are known to be polynomial. And another thing that is known to be doable in polynomial time is finding one correlated equilibrium. In this talk, I will not be focused on finding one correlated equilibrium. I want to find an optimal correlated equilibrium, where by optimal, I mean, for example, social welfare optimal or optimizing any other objective. So finding one is not good enough for us. As for algorithms for optimal correlation, yes.
For the anti-finance, here in this setting, you're assuming that the number of pure strategies is large, it's not fixed.
That's correct. That's correct. I'll be discussing extensive form games. The number of pure strategies in an extensive form game is in the worst case exponential.
What is a very general remark on measured optimization problem that can model as?
You can model SAT actually. The hardest reduction is directly from SAT. So that's why you get the constant error as well.
But SAT is approximate.
Not to within 1/8 or whatever. That max SAT, sorry. Yes. Yes, some constant. Yes. There are known algorithms for this. So there are algorithms based on column generation, or in the team adversarial case, double oracle, that are known, but these don't have real worst case guarantees. These are going to take exponential time in the worst case. And in practice, we also find that even on some rather simple games, it's rather slow. So we want something better. What are our main results? Okay, our main result is going to be that all of these problems can be reduced to solving linear programs with fixed parameter size. What do we mean by fixed parameter size here? And our table of results is going to look like this. And we'll see that for all 4 of these problems, we get slightly different bounds. And this little k and big K, by the way, here, that is not a typo. This is intentional. These parameters are different, as I will explain later. The little k is smaller than big K. So these 4 problems all have different bounds. And so one takeaway that I want you to get from this talk is that all 4 of these problems are different and the bounds are different. And in fact, I'm going to show that some of these bounds are rather fundamental. That some of these differences are rather fundamental. Okay, let's jump in. Yes.
I'm just curious. I guess like it sort of seems like one natural row is missing from that table, which would be like optimal normal form correlated.
I'm going to get to that later. Yes, good question. Okay, so what are games? So in this setting, we will be talking about extensive form games. An extensive form game can be very simply represented as a tree. Here is an example of a tree with a bunch of annotations on it, which I will explain. The edges in this tree are called actions and denote simply the things that agents are allowed to do. The nodes are labeled with the player that acts. So in this case, this is a 3-player game and each color denotes a different player. At orange nodes, it is orange's turn. At blue nodes, it is blue turn. And at green nodes, it is green's turn. This circle node up here is the chance node. And at chance nodes, there is a fixed probability distribution that is known to all players. In this case, I've labeled half-half. So chance plays uniform at random here. And after the game ends, we have reached a terminal node. And at terminal nodes, all players get a utility. In this case, I'm not listing green's utility because in this particular game, I will take green's utility to be the same as blue's utility. This is a team game. Blue and green are on the same team. They get the same utility. Orange is playing against them. This is a 0-17 game. Okay. These dotted lines indicate information sets. What is an information set? An information set simply means that the player cannot distinguish between those two nodes. So in this case, blue doesn't know whether we're at this node or this node when they're picking an action. So to formalize that notion, what is a strategy? Yes. An information set means that a player cannot distinguish between those two nodes. So blue doesn't know whether we're here or here. And I'll explain what that means concretely in a minute when I talk about strategies.
How about an example?
Yes, I'll get to that.
So the players don't necessarily know what chance roll either?
Yes, that is correct.
Yeah, those two trees are the same. The payouts are always exactly the same. So there is no difference between those two.
Down here, the utilities are different depending on what blue plays.
Actually, blue knows what chance.
Blue knows what chance played, but green doesn't.
Those utilities are the same. So you see on the left hand, it says plus, but the bottom left corner is +1,
Yep.
-1, +1. They do it on the right hand side, that's the -1.
Yep.
They're exactly the same. Look at those two green triangles. The left,
Oh.
look below the left, those two green triangles. Yeah, those two four tuples are identical. Therefore, those two panels are exactly the same for the blue player.
No.
It doesn't matter which player who it makes, right?
Okay, sorry.
Panels are the same.
Okay, sorry. The blue can go either left or right here, right? And there are two actions. If blue plays left here, the game ends.
Oh,
If blue plays left here, the game continues. If blue plays right here, the game ends. If blue plays right here, the game continues.
I see.
So you are saying the utility doesn't need to be the same, but it's.
No, I'm making no restrictions on what this utility function can be at this point.
Just to clarify, I assume like every action coming out of a given node is labeled, so during.
Yes.
Okay.
So
that's labeled by direction.
left and right, yep. Okay, so what is a pure strategy? A pure strategy for a given player is an assignment of one action to each information set. And to go back to something that Isaac just pointed out, actions are typically labeled. We will be assuming that it's in each information set, the player has the same actions at each node. So this is a possible thing to do. I'm going to pick one action, yes, not a problem. Yes, let me go one step farther and then hopefully I'll clarify something. Yes, so here is a pure strategy for the green player down here. And what we notice is that the green player must play the same action at both nodes in their information set. So this is an information set for green, and green must play left. Must play the same action here and the same action here. For example, this is not a valid strategy because green is playing a different action at two different nodes in the same information set, but green is playing left here and right here. Does that clarify something about information sets here? The strategy cannot depend. Sorry?
So what does green know about blue? I understand that blue doesn't distinguish between the two, like blue triangles of the left and the two blue triangles of the right. What does green know about?
Well, green cannot distinguish between these two nodes. So green only knows what blue played, but green doesn't know the original chance node.
So green is confused on a different level.
Yes,
And they're not communicating. If they can communicate.
that's correct.
Tell the other one, hey, this is different from that.
That's correct, and that's going to be critical. Yes. Okay, so this is a valid pure strategy because I switched the arrows back. A pure profile is nothing but a collection of pure strategies, one per player in a set. So for example, if I want a pure profile for green and blue, that'll be a pure strategy for blue and a pure strategy for green. A correlated profile is a distribution over pure profiles. Straightforward enough. Okay, now let's talk about adversarial team games. And before I jump in, I have to introduce two assumptions that we'll be using for the rest of this talk. One is perfect recall. So what is perfect recall? Perfect recall intuitively states that a player doesn't forget anything. So on the left here, this blue player is forgetting something. Blue player once knew chance's action and now doesn't. We say that blue doesn't have perfect recall. But if this is green, that's fine, because it's fine for blue and green to have different information as long as neither one of the players is individually forgetting anything. So as I say, blue doesn't forget anything, green doesn't forget anything, we're happy. So on the left, player blue is forgetting something, so that doesn't, and green does. Intuitively, rational agents should not be forgetting things. Seems like a reasonable assumption. The second assumption that we're going to make is timeability. What is timeability? Timeability simply means the information sets don't span across multiple levels of the tree. So on the left here, we have a game that isn't timeable, and on the right, we do. We have a game that is timeable. Intuitively, what this means is that the game has an explicit clock that's encoded in the game tree, and the value of the clock is known to all the players at all times.
So you're saying basically this blue is not the clock perceived one signal step.
Yes.
That's more information.
I'm making an assumption about what the information structure looks like. Right? I'm saying that blue must know how many moves have happened. All players must know how many moves have happened. Okay, so what's an adversarial team game? As I said, an adversarial team game is an extensive form game where the players are partitioned into two teams. Players on the same team must have a different utility. So in this case, I didn't write it on the tree, but green has the same utility as blue. Green and blue are on the same team. A team correlated equilibrium is a pair of correlated strategy profiles, one for each team, such that no team can improve. So each team is doing as best it can against the opposing team. Okay. The first question is correlation even needed to define this concept? One could possibly remove the word correlation from this entire slide and talk about equilibrium possibly if there is no correlation, question mark, is that possible? Well, turns out no, correlation is needed. And indeed, this game right here has no correlated team equilibrium. And I will prove this. No uncorrelated, sorry, I misspoke. Sorry. So let me explain why. Very briefly. So how this game works, nature flips a coin, and then blue tries to communicate the value of this coin to green without revealing the communication protocol to orange. So in order for blue to succeed, blue has to randomize between two possible communication protocols, which means in particular, green and blue have to correlate. This was very brief, but hopefully I give you some intuition for why correlation is needed in this particular game.
Sorry, right.
Yes. Okay, yes. So blue has to communicate one bit of information to green, the value of the coin, right? But blue cannot reveal to orange how that communication is happening, or else orange can win. Because if orange plays the same action as blue, orange just straight up wins. Yes.
Okay, so if you look at the bottom part of the tree, green doesn't know if they're on the left-hand side or the right-hand side. They don't know how the coins split, but they get their payout is solely determined based on if they choose left and they're on the left-hand side or right-hand side.
Yes, green wins. Green and blue win if green's action matches the nature action.
Okay, and then so then we go. So green has no possible way of understanding that except for
this one bit of information that blue can give it.
Because green does know what blue did.
That is correct.
Okay, but if green knows what blue did and yellow also knows what blue's going to do to
Yes.
communicate that,
Yes.
Yellow can
just win.
the side of the tree that will make blue lead.
Yes, that is correct.
Okay, but so any separate randomized strategy where green doesn't like have sort of prior shared information, yellow can do.
That's correct.
So correlation is kind of like prior shared information.
Yes.
Like telling them about a communication protocol before they use it.
Yes, so green and blue are allowed to talk about their strategy before the game starts. And as part of that talking about the strategy, they're allowed to flip random coins that are hidden from the opponent.
Why isn't all one half then equilibrium?
Sorry?
Why isn't all one half equilibrium?
Because then blue isn't communicating any information to green. If I'm assuming you're talking about like everybody plays uniformly at random independently. Yes, that is not an equilibrium because then blue and green has incentive to deviate. In that strategy, if orange guesses wrong, blue and green will only be winning half the time, which is not good. Blue and green should be winning all of the time when orange guesses wrong. Orange should lose this game if and only if they guess wrong. And if blue and green randomize independently, they can't communicate to each other. So they cannot win every time orange gets wrong.
You don't necessarily have to win. You just have to.
Well, if they're not winning, then they can deviate to a strategy that can win, right? They can deviate to a pure strategy that can win half the time against orange's strategy. That strategy itself would be exploitable. But that already means that everybody plays uniformly at random is not an equilibrium.
Why is it not? Because it's a game still. So if we allow people to only flip coins, then there is an option.
There's something key here, and that is on the previous slide, I said no team is allowed to deviate, not no player. So if everybody plays half, everybody plays independently and uniformly at random, no player will have incentive to deviate. That is true, but that is not enough for it to be a team equilibrium. We need no team to have incentive to deviate. And if everybody plays half uniformly at random, then blue and green can establish sort of a communication protocol where blue always chooses the same communication protocol. And if orange doesn't change their strategy, with orange's strategy fixed, blue does better by doing that.
Blue and green together do better by simultaneously shifting.
Yes. To one side or the other. Okay. Okay. So every adversarial team game has at least one team correlated equilibrium, though. And this is going to follow from duality. I will show this in a minute. Okay. So let's briefly talk about algorithms. If both teams have one player, then this is an extensive form team. This is an extensive form game that is 2 player 0 sum. And polynomial time algorithms are known for this setting. Some special teams with special structure look like one-player teams, so-called A-loss games, triangle-free games. I won't get into that, but suffice to say, these games look like one-player teams. And in these settings, you also have polynomial time algorithms because you can reduce to the one-player case. But in general, as I said, even allowing some constant error, it is already NP hard to compute the value of the game. So what do we do? Well, as I said, we want fixed parameter algorithms.
So, one quick question.
Yes.
Is it clear that you can even write down, or when you say NP hard, what is the size of the description of the game?
The size of the description of the game is this object that I have right here. It's the tree.
Okay. So then, is it clear that I can write a correlated strategy in polynomial size in the description?
Yes, by Kerr Theodori, and I'll mention this in a moment. So given a pure team profile, we will say a player plays to a node if the player plays all the actions on the path to that node. Sorry, a team plays to a node. I misspoke. So for example, if this is blue and green's pure profile, then this pure profile plays to these 4 terminal nodes and no others. Right? Because for all of the other terminal nodes, there's at least one action on that path that's not played by the team. The realization form is simply the indicator vector that indicates which terminal nodes are played to by the profile. For a correlated team profile, you take the relevant convex combination. Great. Given this representation,
What is that?
Z is the set of terminal nodes. I have it here. Okay, so given this representation, I can write down a team correlated equilibrium like this. It is a max-min problem where X is the set of realization form correlated profiles for blue and green, and Y is the set of correlated profiles for orange. And A is a payoff matrix. I won't get into the structure of that payoff matrix in this talk, but suffice to say it exists. So we have a bilinear saddle point problem. Great. Now, given this, everything that everything that you were mentioning a moment ago follows immediately. We have duality, we have unique values, we have a representation that can be represented as a convex combination of at most a small number of vertices. So everything is nice. But I haven't answered, like, why are we not done here, right? It looks like we might just be done. And convex duality implies an equilibrium always exists, sorry. We're not done because we don't know how to represent these strategy spaces. Okay, so at this point, since we've separated out the two teams, it suffices to focus on one team. So let's focus on team up. Team down strategy will follow from symmetry. Okay, so for team up, we will remove team down's nodes completely. They don't matter anymore. And we'll think about representing team up's strategy space, X. Well, X is a polytope, right? But it will have way too many vertices and facets unless P equals NP. So we can't represent it directly. What is our main approach going to look like? Our goal is going to be to use common knowledge information to express this polytope as a set of flows on a DAG. Once we have such a representation, this is going to immediately give an algorithm for solving team games. And analyzing the size of this DAG will give fixed parameter bounds on the complexity. And the reason why this succeeds where prior techniques have failed is that prior techniques don't use as intimately the information structure of the team. Yes. Yes.
What's the profile? What does it look like?
A profile is a collection of pure strategies, one per player on the team.
So it's like one out edge from each.
From each information set of the team. So for example, if I go back a few slides, that's a profile. Blue has a strategy, green has a strategy.
And this is being represented
the realization form. Profiles are represented by the realization form vectors.
The realization form of this profile
Is the highlighted black? Yes,
and
exactly.
those highlighted black house completely determine the edges.
That's correct.
and capital X is the set of all realization forms.
Realization forms for correlated profiles, which is the convex hull of the realization forms of all the pure profiles. So now we can take max mins over this.
We're looking at all convex combinations of realization profiles, correct?
Yes. Yes.
So figuring out what set of like out edges, like the out edge representation is straightforward. It's like all possible combinations. But figuring out the set of realization representatives is a very complicated structure.
So this strategy space doesn't have polynomially many facets or polynomially many vertices. You can't enumerate all the pure profiles.
Right. But if we were in out edge land, it would have a simple form.
Out edge land.
Like if we were using the edge representation, it's just all combinations, right? It's a simple poly, so even though it has a constant first.
Yes, this whole thing is a relatively simple looking polytope with exponentially many vertices and exponentially many facets. Okay. So I was here. Okay, so let's jump in. What do we mean by public information? We'll say two nodes are connected if there's an information set of the team connecting their descendants. Okay, so for example, these two nodes are connected. Why? Because there's an information set here connecting a descendant of this node to a descendant of this node. And for this purpose, a node is a descendant of itself. So information sets themselves consist of connected nodes. A public state, a team public state, is a connected component of the graph induced by connectivity, by the connectivity relation. So intuitively, what is a team public state? A team public state encodes knowledge that is common to the team. Once we arrive at a team public state, everybody on the team knows it.
What is the what's it transitive closure of this, right?
Yes.
I mean, it seems like that would collapse to one point or something.
Sorry?
All those D, E, F, and G would all be
That's correct.
collapsed to a point, right?
That's correct.
LM and O would also be collapsed to a point.
LM, N, and O would not be, because
Oh,
L and N can be
that's
separate.
goes up the tree.
Yes, and I was about to do that. These are the public states. So D, E, F, G, as Danny said, is collapsed into a point. L and N are in the same public state. M and O are in the same public state. Okay. Now that we've defined public states, we're ready to define our main construction, which is called the team belief DAG. What is the team belief DAG? Well, since the whole thing is too complicated to write down on this page for this game, I won't be doing that. Instead, I'll be focusing in on one public state.
This is a tiny, tiny game.
Yes.
Sorry.
This structure's pretty big. So let's focus on this public state. For this public state, the piece of the team belief DAG that corresponds to it looks like this. Okay, I'll explain what all of this means. We have two different types of nodes and two different types of edges. A belief. So the black nodes I'll call beliefs. A belief is a subset of the public state that a team may play to. So in this case, if I look at this public state here, the team hasn't made any decisions yet. So by definition, the team must play to all four of these nodes. So there is only one belief in that public state, namely all four of these nodes. The edges out of beliefs are called joint actions, and a joint action simply encodes one action for each information set represented by that belief. So in this case, in this belief here, D, E, F, G, there are two information sets, and so 2 times 2 equals 4 joint actions. If there would be 3 information sets with 2 actions each, there would be 8 joint actions, so on and so forth. And this is where we're going to get our exponential dependence, and this is where we're going to get the parameter that we need to bound. Okay. If you take a joint action from a belief node, you reach an observation node. An observation node is simply the set of nodes reached by playing a joint action at a belief. So, for example, if I'm in the belief node D, E, F, G, and I take that joint action, I reach those 4 nodes, which means L, I, and K is an observation node right there. The edges out of observation nodes are called observations. And at an observation node, the team observes the next public state and obtains the next belief node by restriction. So for example, at L, I, and K here, I can observe the public state Ln. And if I observe the public state Ln, I restrict Li and K to Ln, and I get Ln. It is possible for me to play to L but not N, in which case, if I restrict to this public state, I will get only L, so on and so forth. You can see some of that in this diagram here. Okay. And what is useful about this DAG? Well, turns out, and I won't prove this, but maybe some of you already have an intuition for how this might go. The flows on the DAG correspond exactly to team correlated strategies. And therefore, the set of team correlated strategies is given by a constraint system that basically says the flow into any given belief node is equal to the flow out of it. Now, the whole point of writing flows in this way is that we can come up with the following bound. Right now that we have this, we can plug everything into the LP that we had before, and we get that adversarial team games can be solved by an LP of size number of edges in the DAG. Well, the number of edges in the DAG turns out to be basically equal to the number of nodes in the DAG. And by number of nodes, right? And why is this so, right? Because if we look at any observation node here, every observation node has exactly 1 edge into it. And at most as many edges out of it as there are public states. And there are most as many public states as there are nodes. So we're happy. And the number of nodes in the DAG is at most equal to the number of observation nodes in the DAG times some fudge factor. Why? Simply because the observation nodes are at most the number of belief nodes. Each observation node corresponds to 1 belief node at most. Okay, so our goal now is going to be to bound the number of observation nodes. How do we do this? A private state. A private state is the list of information sets and actions played by a player on a path to a node. A private state simply encodes the information that a player knows, and an individual player knows. So in this case, I'm just going to write down the private states of all players that are all non-terminal nodes right here. Let's take an example. I'll take this node M right here. Sorry. I'll take this node M right here. And at this node M, Blue's information is that Blue has reached information set DE, and at that information set has played left. Green's information is that Green has reached information set MO, and at that information set has done nothing, hasn't played an action yet. The team information complexity is the largest number of private states across all players in a team in any team public state. And this is going to be our parameter. Intuitively, a high team information complexity means that lots of information is split among team members that is not common knowledge. Right? It is sort of the gap between public information and private information. So in this game here, we have k equals 3. Why? Because it turns out in all 3 non-trivial public states, there are exactly 3 private states. There are 3 here, 3 in this information set, and 3 in this information set. Now that we've defined the parameter, we can start bounding stuff. And indeed, bounding stuff is going to take exactly 1 slide. Given a team public state, for each private state, either the player doesn't play to that private state, or the player plays to the private state and then picks one of the actions available there. One of these 2 things happen. And that information is already enough for me to exactly determine a belief. The purple parts determine the belief. And the red parts determine the joint action. So once we have a belief and a joint action, we have an observation node. Okay. So this is enough for me to select an observation node from all the observation nodes in our data. So all we have to do is count the number of ways that we can do this. Therefore, the number of observation nodes in every team public state is at most b plus 1 to the k, where b is the branching factor of the game, and k is this information complexity parameter. Therefore, for the whole problem of solving adversarial team games, we get an O star of b plus 1 to the k algorithm. B plus 1 to the k, sorry, LP size. Okay. And now to emphasize here, since we've backed up now from one team to now constructing the DAG for both teams, this parameter k is the larger between the 2 teams. Now we'll discuss the second part of the talk, which is general sum games. But before I do that, are there any questions? Yes. The plus 1 comes from the fact that there are b choices here and 1 choice here. Yes. Yes. So I can either pick one of the b actions there, or I can avoid the node altogether. That's an extra choice. Okay. General sum games. So the question is, does a similar idea work for correlation? And the fact that I'm asking the question means that you probably know where I'm going. Yes. So I won't have time to go through the entire proof for this section. So I'll just sketch the proof. But before I do that, I'll give you a precise formulation of what is correlation in general sum extensive form games, which is what some of you have been waiting for quite some time. So let's get into it. Reminder, a correlated strategy profile is a distribution over pure profiles. And now we're going to be considering correlation over all the players at the same time. So before we were saying each team is going to randomize independently. Now we're saying all the teams are random, all the players are randomizing together. And as I said, there's going to be this notion of a mediator. And this mediator is going to take a correlated profile mu and sample a pure profile from it, hidden from all the players. Now, the game begins. When the game begins, let's say we reach a node A first. And the mediator's pure profile says at A, you should go left. So the mediator is going to go up to the blue player and say, hey, blue, you should go left. And blue might say, okay, and go left. Now, it's orange's turn. And the mediator may look into the pure profile and say that orange should also go left. And so the mediator goes up to orange and says, orange, you should play left. And orange might say, nah, I don't want to. And so we'll just completely disobey the mediator's command and go right. And that's fine. The players are free to disobey the mediator if they so wish. Now it's blue's turn again. Mediator might say, blue, you should play right. And blue might say, okay. And then we reach this node. And at this node, orange has already disobeyed a mediator command. And the rule that we will instate is that once a player deviates, they no longer receive recommendations. So here, orange no longer receives a recommendation. Orange is sad because they don't get a recommendation, but they still have to pick an action. Let's say they go right. And let's say the game ends. Okay. A correlated equilibrium intuitively will be a correlated profile from which no player ever wants to deviate. And the question that I want you guys to think about is, when is a player allowed to deviate? And the answer to that question is going to be what distinguishes our multiple notions of correlation. If a player, yes?
Sorry, before we get into that, so in the previous world, we allowed like prior communication.
Yes. Yes.
Now, there's no teams.
There's no
So
teams.
we allow no prior communication.
That's correct.
Everybody has to have independent random strategies, except through information like that from the media.
Yes. But it'll actually be stronger than that. The condition that we'll want is that the players don't do anything different from what the mediator says. We will want a mediator strategy that the players are always incentivized to obey.
So our classic strategy of consideration is they're only correlated for the mediator.
Yes.
And then we're trying to guide that to they just follow the mediator.
Yes. Okay. So when is a player allowed to deviate? If the player is allowed to deviate at any time, we get the strictest notion of equilibrium that we will be looking at here, which is an extensive form correlated equilibrium. If the players are allowed to deviate before receiving a recommendation, but once they receive a recommendation, they are bound to play it. This is a so-called extensive form course correlated equilibrium. And if the players are only allowed to deviate at the start of the game, this is a so-called normal form course correlated equilibrium. So now we've defined three notions of equilibrium. And now I'm ready to address the question of where is the fourth notion? So as some of you may know, there is this notion of normal form correlated equilibrium, or simply correlated equilibrium, as it is commonly known in the earlier literature. Our model doesn't handle that. And the reason why our model doesn't handle that is because in normal form correlated equilibrium, the player is given the entire strategy up front. The player is told everything they should do at every single information state up front at the beginning of the game. That does not gel with what we just presented. So our model doesn't fit into that. In fact, normal form correlated equilibrium is a strictly harder problem. No one even knows whether one can be found in polynomial time. That's a pretty big open problem. Okay, so one question, are these three notions even different? And it turns out, yeah, yes. 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 If they say they're going to deviate, then no recommendations. If they don't say they're going to deviate, then they better obey every recommendation. Yes.
I'm still not sure why someone would want to deviate from the mediator.
If deviating from the mediator gives them a higher utility and expectation, then they'll deviate.
Do they know what the mediator is about?
They know the mediators, they know mu. They know mu, but they don't know the specific strategy pi that was sampled from mu.
But they can, given the history of the suggestion, they can like.
They know what they have been suggested in the past, and they know what they are being suggested presently. They don't know anything else.
So they can kind of figure out what the pi is.
They could.
And then perhaps then.
They could.
Say that is the bad type of mediator.
Yep.
So
Yep, that's
at
fine.
any point of time, I have revealed some information about the pi sample.
Yep.
And I could compute my conditional expectation of utility.
Sure. And if I can do better than that conditional expectation, then I will deviate. Yep. So if a player is not incentivized to deviate ever, then we are in correlated equilibrium. So are these three notions even different? And it turns out, yeah. So here's an example game that we were running experiments on. And we can see, indeed, in this example game, what I've plotted here is the space of possible payoff profiles. So on the y-axis here, we have player one's utility. On the x-axis, we have player two's utility. So this point here, for example, means that in normal form course correlated equilibrium, it is possible for player one to get utility 3.75 and player two to get utility 3.32 or whatever. And as we can see, each polytope is strictly contained in the next one. So all three notions are strictly different in this case. Let's talk about algorithms again. I mentioned this before, but just to refresh. Yes. Yes, and I'll have these up later on as well.
So the intuitive reason why the stricter, the ones toward the top of the list, there's a smaller range of possibilities is like if the players have more opportunity to deviate, then the mediator has to like restrict the smaller possibilities.
Correct.
To keep them all
Correct.
going along with whatever it's suggested.
Correct. Exactly. So let's talk about algorithms. Finding an arbitrary extensive form correlated equilibrium can be done in polynomial time. But as I said, finding one, even approximately, is empty hard. Our goal here will be to find an equilibrium that optimizes the expected value of some objective function. So here you can think of it as the mediator also has some objective function over the terminal nodes. And the mediator wishes to optimize that objective function. So one example of this is social welfare. The social welfare is the sum of all the players' utilities. That's a simple enough objective function to write down. And we can think of one special case here as finding a social welfare optimal equilibrium. Okay. And as usual, we will be looking at fixed parameter algorithms. So we're trying to find LPs of size O star B to the K, maybe something like this. And you notice I've switched to a capital K now. Why have I switched to a capital K? Because in the team setting, our lowercase k was dependent on the team. Now we don't have teams. So capital K is the information complexity for the quote unquote team of all the players at the same time. So this is information that is public to the whole team, and the difference between that public information and the private information of each individual player. So this parameter big K is going to be bigger than the parameter little k that we had earlier. Right? And our main idea is going to be to generalize everything that we did in the team case to correlation. And I'll only sketch the proof at this point because I'm running out of time. An optimal correlated equilibrium can be expressed very similarly as before as a linear program. I won't get into that. And as usual, we will be trying to represent the strategy space. So turns out we can do a very similar thing. We can construct a very similar looking DAG. What's different about it compared to the team belief case? In the team belief DAG, if we are at this public state here, quote unquote public state, which is just a terminal node, and we have had this playthrough, in the team belief DAG, right, the strategy said to play left at B. So the team belief DAG doesn't, so in the team belief DAG, the belief at this public state is empty. But for the three notions of correlated equilibrium, we will actually have something non-trivial here, because in correlated equilibrium, we have to care about the possibility that a player might deviate. For normal form course correlated equilibrium, we have to denote which player deviated. For extensive form course correlated equilibrium, we'll have to note not only that, but where the player deviated. And for extensive form correlated equilibrium, we will need not only those two things, but we will also need what recommendation the player was given when they deviated. So we need more and more information in all three of these settings. So in teams, recall there were B+1 choices for private state, where the +1 came from the fact that the player wasn't recommended to play to the private state. For our three notions of correlation, these are going to change. For team games, that's all that matters. But for normal form course correlated equilibrium, the only thing that changes, in fact, is the little k to big K. So for normal form course correlated equilibrium, knowing that a player wasn't recommended to play to a private state is already enough. So nothing changes. We only get this little k to big K change. For extensive form course correlated equilibrium, we need to know where the player deviated, which is why we lose this extra additive D. Right? We lose an additive depth of the game tree. Right? For extensive form correlated equilibrium, we not only need to know where the player deviated, we also need to know what they were recommended when they deviated. So in this case, there are not B plus D choices, there are B times D choices. And these are the three bounds that we promised at the beginning. Okay, let me summarize quickly. These are all the results that we've proven here, at least very briefly. A team correlated equilibrium can be solved with an LP of size B+1 to the K. Normal form course correlated equilibrium can be solved with a slightly bigger linear program. Extensive form course can be solved with an even bigger one with an added parameter. And extensive form correlated equilibrium can be solved with an even bigger one. Okay. And one thing that I want you guys to take away from this, as I mentioned earlier, is that these four problems are concretely different. Right? I've had different bounds for each of these four problems, which is not really something that prior work has shown so clearly. Now, how fundamental are these bounds? Well, the first two here are separated by definition, right? Little k and big K are different. You cannot define little k in a non-team game. Little k is smaller than big K, so we get a smaller bound. The second bound here is actually computational. And I didn't show this in this talk, but we can prove a lower bound that says you cannot have a fixed parameter algorithm in only B and capital K for extensive form course or extensive form correlated under reasonable assumptions. We leave open the question of whether this third gap is fundamental. There's only a quadratic difference here, so this will be a much harder thing to show if it is indeed true. Okay. I'll briefly talk about some experiments now. You should focus on this middle column here because this middle column is our new algorithm, and as you can see, it on these like small sort of games that we were testing, it blows everything before out of the water, except on this game here. And you can guess what is happening in this game here, or you can look a couple columns to the left. K is big. So what do you expect? And in optimal correlation, we get a very similar story. The moment K gets too big, we fail, but before that, we are very fast. Okay. And to conclude, Some of these games here represent basically general sum multiplayer games that in which the players are colluding. So I have a bunch of players on one team and a bunch of players on another team, and they're colluding against each other. One of these games actually represents a small end game of bridge. And in these games here, we have various sorts of like conflict resolution or a ride sharing game on a particular graph, things like this. Okay, to conclude, I'll briefly talk about some future ideas. Are there more practical algorithms based on similar ideas that don't require you, for example, to write out the entire DAG up front? And one thing that I didn't elaborate on in this talk at all, but there are these prior special cases that we know can be solved in polynomial time. Our construction does not subsume those. So we leave open the question of whether there exists a construction that is able to simultaneously have these fixed parameter guarantees and subsume these earlier constructions. Is there an extension to normal form correlated equilibrium? This is again a major open question in the field. Is it possible to solve for normal form correlated equilibrium in polynomial time? And the final question that I want to leave open is the gap between these, is the gap between extensive form coarse and extensive form correlated somehow also fundamental, which requires some sort of fine-grained complexity analysis because the gap is only quadratic. And that's all I have. Thank you. Any questions? Yes.
You mentioned ride sharing
Yes.
game.
Yes.
Why is that a game? I guess because the driver or the app is trying to optimize one thing, whereas the customers want something else to optimize.
Sure. Yeah. So the drivers themselves have incentive to try to pick up as many drivers as they can, passengers as they can, for example. And the mediator might want to optimize maybe their own profit or social welfare or anything like this. So the drivers have slightly different incentives from the company here. We're thinking of the company as the mediator.
And of those games, how big are these LPs that you're solving, and what solver are you using?
The solver was Gurobi. The LPs have size order of, I think, tens of millions or tens of millions of non-zeros. These were solved on our labs cluster.
You have a cluster here?
Yeah. My advisor has a cluster that we use, yes. Yes.
So I was trying to think about, seeing correlated games. I'm thinking about bridge.
Yes.
I think what you're describing in bridge is cheating.
No.
In bridge, you're required to publish your correlated strategy. And if your opponent's team asks you, like, how are you communicating information, you have to tell them, honestly. So does that mean it's like not in this world? Because this is all about private correlated strategy.
Oh. Wait, you have to tell your opponent how you're communicating information.
Yeah, that's the system, right? Yeah, you have to tell people how your bidding system works, how your card signaling system works, and if you don't tell them, that's. Yeah.
Can I tell them after the game?
No, they ask you after every bid, like, what did that mean?
Oh.
Well, they don't ask the player who did it; they ask the partner to more precisely get that information.
I see.
But okay, so are there common games where like the secret correlation is a key part of the game?
In that case, I don't know. We were thinking of bridge as an application of this. At least for example, I'll say this. In typical, I think like computer tournaments for bridge, this restriction does not exist. Okay. You are allowed to communicate however you want and not reveal it.
One bridge bot against another
bridge
bot. Okay.
Yep.
Maybe they use some of their rules.
Yep.
Cool.
How tight do you think your LP size
That is hard to say. There are probably polynomial factors that can be shaved. As for the exponential term is reasonably tight under reasonable complexity assumptions. So, for example, there are games for which k is like theta n, and for those games, assuming something like strong exponential time hypothesis or whatever, you can't do too much better than 2 to the theta n.
I just want to clarify. So your fixed parameter is this parameter just k or something else?
B and k for the teens case and the normal form correlated case, and DD and K for the extensive form case. So they're all the things that appear in this exponential term. But one thing that I want to note is that the only exponential dependence is on this K. The only exponent is this K.
Could you go back to this, the list of experiments that you had?
Yes. This one or this one?
So the times are mostly a few seconds, but
Yeah.
oh, there's one 48 minutes there.
Yeah. So basically, one thing that I want to note here is with these things, more or less, if with team games at least, which is the easiest of the cases that we discussed, more or less, as long as you can write it down in memory, it's more or less instant. You can do it in under a minute. For correlation, not quite, but still pretty fast. And so the roadblock at this point is memory. The roadblock at this point is memory. So if there's a way not to write down the entire DAG, for example, generated incrementally, which there probably is some way to do this, but we're working on that, then that would greatly speed things up.
If there aren't any more questions, let's thank Brian and for the talk.